Have you ever wondered what could happen if we combine AI and quantum computers? It's both exciting and scary. Quantum computers are incredibly powerful and can solve complex problems much faster than regular computers. But there's a catch. Renowned physicist Michio Kaku has discovered something terrifying, and it could lead to the extinction of humanity. Join us as we explore the world of quantum computers and AI, their revolutionary potential, and the shocking warning from Michio Kaku. Quantum computers are exceptional computers that revolutionize computing by operating on the principles of quantum mechanics. Unlike classical computers that use bits to store and process information, quantum computers utilize quantum bits, which are commonly called qubits. While classical bits can only be in two states, 0 or 1, qubits possess the incredible ability of superposition. This means that a qubit can exist in multiple states simultaneously, representing both 0 and 1 at the same time. This is not just a little advancement in the basis of computation. We are talking about a large leap that provides possibilities for solving highly complex problems that our modern computers are limited to. The power of quantum computers lies in their capacity for parallel computation. By exploring different states and possibilities simultaneously, they can potentially solve specific problems much faster than classical computers. Undoubtedly, there is a widespread debate about the use of this revolutionary system. At first, you could liken it to the regular developments we are making on classical computers, increasing the processing power of a single chip. But the argument here is quite different. The improvement comes from the basic unit of computing. Quantum bits outperform classical bits, and this leads to the wide gap between the processing power of quantum computers and conventional computer systems. Now let's walk through the history of this invention. Quantum computers have a rich history dating back to the early 1980s when physicist Richard Feynman introduced the revolutionary concept of quantum computation. Feynman envisioned a new kind of computer that could leverage the principles of quantum mechanics to tackle complex problems beyond the capabilities of classical machines. However, it wasn't until the 1990s that significant breakthroughs in this field began to emerge. Back in 1994, a mathematician named Peter Shor, working at Bell Labs, unveiled an algorithm that sent shockwaves through the scientific community. This algorithm was a game-changer for quantum computers because it had an incredible ability to efficiently factor large numbers. Now you might be wondering why factoring numbers is such a big deal. Well, it turns out that factoring plays a crucial role in many encryption methods used to protect sensitive information in our digital world today. Shor's algorithm opened up a whole new realm of possibilities and sparked both excitement and concerns among scientists. It showed how powerful quantum computers could be in breaking the encryption systems we rely on. So, throughout the 1990s and early 2000s, researchers rolled up their sleeves and started exploring different ways to build practical quantum computers. One of the most promising approaches involved tinkering with individual atoms or ions to act as qubits, which are the building blocks of quantum computers and are the fundamental units of information in quantum computing. In 2001, a group of scientists at IBM achieved a major breakthrough. They successfully demonstrated the concept of quantum computing by using nuclear magnetic resonance to control qubits. Think of it as an eureka moment in the world of science. This achievement showed that quantum computation was not just a wild idea, but something that could actually work. It lit a fire under researchers, pushing them to progress even more. As time went on, scientists made incredible strides in developing stronger and more reliable qubit systems. They explored different types of qubits like superconducting circuits and trapped ions, each with its own set of advantages and challenges. They were trying out different tools in a quantum toolbox to see which worked best. All these advancements paved the way for the construction of increasingly powerful quantum computers. The number of qubits kept growing, allowing for more complex calculations and simulations. It's like going from a basic calculator to a supercomputer. Later in 2013, something great happened. Google and NASA joined forces to create a quantum computer called the D-Wave 2. Picture it as a high-tech powerhouse that was going to be housed at NASA's Ames Research Center. But guess what? A government shutdown came along and threw a wrench in the works. It disrupted the project and stopped the quantum computer from reaching its full potential. Why? Well, it had to do with worries about the potential risks that could come from using such an advanced computing system. Even though the computer was up and running, the shutdown put a halt to further progress and plans until NASA could get back on track. Fast forward to 2019, and Google once again captured global attention, solidifying its place at the forefront of technological innovation. This time, the company made headlines with a monumental achievement in quantum computing, known as quantum supremacy. Using their cutting-edge quantum processor, aptly named Sycamore, Google demonstrated the incredible potential of quantum computers by solving a complex mathematical problem that would have taken even the most advanced classical computers thousands of years to crack. To put it into perspective, the Sycamore processor tackled this daunting task in a matter of seconds, an astonishing feat that left scientists, technologists, and industry leaders in awe. Quantum supremacy represents a critical milestone in the field of quantum computing, marking the first time a quantum computer conclusively outperformed a classical computer in a specific task. This breakthrough was not just a theoretical exercise, it showcased the immense computational power and speed that quantum machines could bring to solving problems in fields ranging from cryptography to material science and artificial intelligence. Google's success with Sycamore sparked excitement and optimism about the future of quantum technology. Suddenly, what once seemed like futuristic speculation now felt tangible and within reach. The achievement galvanized researchers worldwide, leading to increased funding and heightened competition in the race to develop practical, large-scale quantum computers. In 2020, IBM followed Google's groundbreaking achievement with an announcement that sent shockwaves through the tech world. The company unveiled the IBM Q System 1, a fully integrated quantum computer explicitly designed for commercial use. This remarkable machine was not just a proof of concept or a research tool, it was a polished product meant to bring the power of quantum computing into the hands of businesses and researchers. Encased in a sleek, futuristic glass enclosure to protect its delicate components, the IBM Q System 1 symbolized a leap forward in making quantum computing more accessible and practical for real-world applications. Imagine a world where businesses, scientists, and innovators could have a quantum computer at their fingertips, capable of tackling problems that classical computers could only dream of solving. With the IBM Q System 1, that vision started to come to life. Companies could explore applications in areas like drug discovery, optimizing supply chains, financial modeling, and much more. IBM's announcement also marked a shift in quantum computing from being a niche research area to becoming a mainstream technological pursuit with tangible benefits. The rapid advancements in quantum computing did not go unnoticed by governments and industries worldwide. Recognizing the transformative potential of this technology, many nations began to invest heavily in quantum research initiatives. Governments allocated billions of dollars to establish state-of-the-art quantum research centers and labs, aiming to foster collaboration between academia, industry, and public institutions. These centers became hubs of innovation, bringing together some of the brightest minds in physics, computer science, and engineering to tackle the challenges of building more powerful and reliable quantum systems. Industries also jumped on the quantum bandwagon, eager to capitalize on the opportunities presented by this groundbreaking technology. Tech giants like Google, IBM, and Microsoft ramped up their quantum research efforts, while startups specializing in quantum algorithms and hardware began to emerge. Collaboration became a key strategy, with companies partnering with universities and research institutions to accelerate progress. The race to harness the power of quantum computing turned into a global effort, with countries like the United States, China, and members of the European Union vying for leadership in this critical area of innovation. These developments marked a new era for quantum computing, where the focus shifted from theoretical exploration to practical implementation. The excitement surrounding quantum technology was palpable, as researchers and policymakers envisioned a future where quantum computers could revolutionize industries, solve previously unsolvable problems, and reshape the way we think about computation itself. The journey of quantum computing, from its humble beginnings as a theoretical concept to its current status as a transformative technology, continues to inspire and captivate minds across the globe.